Alright, so welcome back to particle physics and the Standard Model. This is lecture 52 and in the last class we finally finished deriving our master formula for the cross section, right. We took the transition amplitude, identified the matrix element in that and worked out what this Lorentz invariant phase space was that was sitting in the expression for the probability for the incident particle to scatter, right. And then we put all these moving parts together to finally obtain the differential cross section in terms of the Lorentz invariant phase space and removed the other Lorentz, the Lorentz variant parts outside, correct. And we identified that the amplitude squared encodes the dynamics of the problem. Ultimately you can trace this back to the Lagrangian, right, and the rest of it encodes the kinematics of the problem, the energies and momenta and velocities and masses and so on. And we saw one special case of 2 to 2 scattering in the center of momentum frame where things simplify. We work this out, we put in all the correct change of variables and all that and obtain this simplified expression in the end, right, which has all the correct ingredients. You have 1 over energy squared, the center of mass energy squared, that gives the correct dimensions also to the cross section, to the differential cross section here with respect to solid angle, and the m square again encodes all the dynamics. If that is large then the transition rate is going to be large, and you had the theta function ensuring that you put in the correct amount of center of mass energy to produce the final states, right. Okay, so in this class we are going to move on to the notion of decay, but before I do that let me point out one little important thing which we will use again in decay. When we wrote the differential cross section, see there was a virtue in separating out the Lorentz invariant phase space. Okay, why is that? Put differently, is the cross section a Lorentz invariant quantity? Of course it is not, right. It has units of centimeter squared, okay, that is not the most important thing, but it is not, okay. You go to a different frame, you may, so we do know there is length contractions are real things. So in a different frame you might look at the object in a more squished way or in an elongated way, and over there you will measure the cross section differently, right. That is exactly what is encoded here. So the relative velocity down here in the denominator, that is Lorentz invariant, of course. The Lorentz invariant phase space is explicitly Lorentz invariant, but the energies are not Lorentz invariant, right. And similarly the m squared up there could contain terms that are not necessarily Lorentz invariant, okay. You generally try to write it in a Lorentz invariant way, but this E1 and E2 down here should tell you the cross section is not a Lorentz invariant, okay. So we will see this concept rhyme in the concept of decays also, okay. So I am going to write down decays, okay. So you can think of decays as 1 to n scattering, okay. So what is a decay after all? You have a particle coming along and then it disintegrates into some n number of final states, right. So as far as deriving expressions are concerned, right, for the decay rate, you can just think of it as 1 to n scattering. What do I mean in particular? I can still use the notion of a probability or a differential probability for decay to happen divided by time. That literally is my decay rate, okay. Again, just to be clear, this is the probability for the scattering to happen in this case, or in this case for decay, okay. So once again we can go through all the song and dance of how to obtain that differential probability, now we are just going to restrict ourselves to the case of one particle in the initial state, so that I can right away write down the master equation for decay, which is this. This is one particle in the initial state. Again, I do have a transition amplitude, and hence I have a matrix element to talk about, and again I have a d ellipse. Okay, that's it actually. That's the master equation for decay. Okay, so d ellipse is once again you would take the final state, however number of particles you have in the final state. If you have 2 particles in the final state, this is exactly what d ellipse is, the Lorentz invariant phase space. You will have a P2 and a P3 in this case. That's how you would label it, right? Okay. Now there is so this is a general formula, but let's now look at 3 or 4 useful concepts, okay, of decay. Okay, so decay is something you would have studied since high school, right? Radioactive decay, right? Decay rate, decay half-life, lifetime, etc., etc., right? So all of these notions are exactly the same here also. It's just that we are seeing it from a more sophisticated point of view, from a quantum field theory point of view. Okay. So if there were multiple channels, okay, to decay into, particle need not decay to only one set of daughters, we know this, right? For example, the pi plus can decay into the mu plus with a muon neutrino. It can also decay to a positron and an electron neutrino, right? Or if I take a W, it can go to so many different final states, right? It can go to a C bar B, or a C bar S, or a D bar U, right? Or leptonic channels, right? So I can have electron channel or a tau-on channel, and so on and so forth. Can even have 3 body decays, 4 body decays, and so on, right? To give another example, pi 0 can decay, it's mostly it goes to photons, but it can also go to E plus E minus and so on, right? When we have this, we can of course write the total decay width, okay? There's a reason this is called the width. Let's not get into it now. Sometimes I might use that word. Just think of it as total decay rate, okay? The total decay rate is the sum of the rates for each channel. You have to compute this using this for each channel and just sum them up. That's it. Very intuitive, right? So plus dot dot dot, where A, B, C dot 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 are channels. Okay. So this gives us a notion of the branching fraction. Why branching fraction? You can think of each channel as a branch that is available for the initial state to decay to, right? So branching fraction of a given channel alpha, it's nothing but, so it's also called branching ratio, that's why I write BR. That is the decay rate of that particular channel divided by the total decay rate. Okay, so if I sum them all up, of course I have to get 1, right? So why is this important? Why this weird quantity is important? Because this is directly measurable. Okay, even if I don't know the total rate, right, of a particle, I can see, let's say 20% of the time it goes to one final state and 80% of the time it goes to another final state. That at least I can measure, even if I don't know the actual decay rate, right? So this is a much simpler thing to measure, and also it is very important. The exact branching fractions to the final states is an important fingerprint, okay, to identify particle species. Okay, for example, this is exactly how. So we haven't really measured the total decay rate of the Higgs boson. Okay, but we did measure the various branching fractions, and that measurement was super important to really nail down the fact that we discovered not some imposter, but really it was the Higgs boson. Okay, this clearly is an, pinpoints the identity of the particle that you are looking for. Okay, all right. So in your assignments there will be one or two questions based on these branching fractions. It's a very simple notion, right? Okay, so let's look a little bit more about how these the decay rates go. For example, suppose I have, okay, a Lagrangian with 3 different scalars, okay, an interaction among 3 scalars. Okay, let's just call it, what do I call it? So in my notes I've called it, let's call it just phi 1, phi 2, phi 3. Okay, let's just put it this way. Okay, and the idea here is that phi 1 decays to phi 2 plus phi 3. Okay, now this can't be the entire Lagrangian. I have to give it a coupling up front, right? So that coupling, let me call it G phi, but I'm going to slightly, in my notation I'm going to make it a capital G phi. Okay, why am I doing that? Because in the Lagrangian I need a dimension 4 term, right, and each scalar carries a dimension of 1, energy dimension 1, right? Necessarily that means the coupling, and maybe I can write the coupling alone in red, the coupling is a dimension full coupling. It's not like the gauge coupling, it's not a small g. To indicate that it's dimension full, I am giving it a capital letter. Okay. Now with this in mind, we can immediately write out what d lips is. That's nothing but this, simply that, okay, over ECM, where PF is the final state momentum. So we can now think of the rest frame of the mother particle, so that in the final state both the daughters have the same momentum, right? So what is ECM now? It's a center of momentum energy, right? So that just means it's the center of momentum energy of the final state particles if you want, so that m phi 1 is what ECM is up to a factor of 2, right? Half of ECM is m phi 1, and through energy conservation this is nothing but 2 times m phi 2 squared plus pf squared. right. So all said and done, basically if I do an integration of d-ellipse, right, so this is not something I am going to really work out for you, unlike in the previous cases, because I worked out a lot of tedious algebra for you. You can now easily go back and do, this is a much simpler integration to do now, okay, much simpler to change variables, use the correct integration and so on. I am just going to write out the final expression which looks like this, okay. So phi 2 squared over m phi squared, but under a square root, but that is not all. This is for m phi 2 equals m phi 3, okay. This is for the case of equal final state masses. That simplifies the expression that I am writing down, okay. So with this I get the decay rate goes as this g phi squared divided by 32 pi m phi, okay. Why? Because I have ECM, right, in the expression, which is nothing, okay. So I have E1 in the expression, right, below the m squared, and that is nothing but the mass, right. So that is what I have written here, and the 2 multiplies the 16, I get 32, and I have 1 minus 4 m phi 2 squared. So this is m phi 1, of course, this is also m phi 1 divided by m phi 1 squared, okay. So I went to the trouble of writing this expression down because I wanted to highlight a couple of things, okay. First of all, notice that the it has the correct units, right. The coupling had units of 1, mass units of 1, right, and since this is a decay rate, I have to square the amplitude will contain the coupling, right. So I have the square of the coupling, so necessarily it means I have to compensate with some mass in the denominator, and that is what has happened here, correct. And what mass could it be other than the mother's mass, right. So that is what I have done, that is what we get here. The other interesting thing is the phase space integral has made sure that if if m phi 1 was less than 2 m phi 2, then this will not work out, there is no decay rate to talk about, right, because it is under the square root and all that, correct. So this part is sometimes again colloquially called the phase space part, because that is where it comes from, okay. And it shows that if m phi 2, if the daughter mass is very close to the mother's mass, then the decay rate is going to be suppressed, right. Whereas if m phi 2 is much smaller than m phi 1, that is if the daughter mass is negligible compared to the if the daughter is almost massless, or even if it is literally massless, right, then you get g phi squared over 32 pi m phi 1, that is it. The phase space is maximal now, it is just 1, right. Okay. So this is just what I wanted to highlight about decay rates with one simple example, okay. Now let us move on to an example that is a bit more complicated, alright, and that would be muon decay. Okay. So, what is the primary channel for muon decay? It's a weak decay. So, I have muon going to electron, electron antineutrino, and muon neutrino. Alright. So, let me go into a little bit of detail to show you how this goes, and then I'll write down the final expression. Okay, and we'll inspect that final expression soon. So, that bit of detail is when you write the squared amplitude, okay, you have to be a bit careful about the spins of the states that you are considering. Okay, so people call this summing over the spins. Okay, so I'm going to put that in quotes. All right, but I've also done an average, right? So in particular, what this means is you have to actually average over the spin states of the mother, in this case the muon. Okay, but you would sum over the spin states, okay, of the daughters. Okay, because after all you have to account for every spin that the daughter states could take, right? That's ultimately what determines the total cross section. But the muon could come with spin up or spin down. You have to average over both those. Okay, these are all different states, right? You have to actually account for each state when you compute the amplitude and hence the cross section, right? So there's a certain way to do this, and this course is not really designed for that, okay, to teach that. But for the curious, you can go to any quantum field theory textbook like Schwartz, and you can see how you can put spinors together to average and sum over spin states. Okay. So, but I am just going to write down the expression for this. Okay. Just to give you a flavor for how these things look like when you put spinors together, and then and then you work out the spin sums and average, you get terms like these, momentum dependent terms, dot products of 4 momentum. Okay. So what is GF? That's the Fermi constant. Okay. Remember we saw this when we talked about neutrino oscillations, for example, right? So that comes from, you know, the Lagrangian written this way. It's a contact interaction that Fermi had famously written down to account for beta decay plus the Hermitian conjugate. Okay, but now we know the modern interpretation of this GF. Okay, that's nothing but 1 over V square, where V is what? The Higgs web, which is 246 GeV. Okay, so how do we know this? Because we know that secretly, Fermi, in Fermi's time, he didn't know what was going on in the vertex, so he wrote down a contact interaction where you had a muon, spitting out an electron, right? With these, so this was the vertex that he was thinking about, but we know that secretly this comes from vertices like these, right. We know that ultimately this is the fundamental vertex for muon and anti-muon neutrino. This is another fundamental vertex, right. So, we put these together and then get the contact interaction vertex, right. So, that is exactly what we saw when we did electroweak symmetry breaking and etc., etc. Okay. So, that accounts for the GF, but of course, we have to also do integration over phase space. Once again, that is not something I am going to do right now, okay, because it is not a trivial calculation at all. You have to do a d-ellipse integration for a 3 body final state now, as opposed to a 2 body one we just saw, right. But all said and done, we are going to get an expression that makes sense once we look for the sense making bits, okay. It will look like this. So, mu to the 5, then there is a 192 pi cubed, okay. Why does this make sense? Because what is the units of GF? You just saw, right. I wrote it as 1 over V square. Also it is the coupling in front of a dimension 6 operator, right. They are all the same thing. So, the units of that is -2, right. But what is the units of a decay rate? That is minus, that is +1, right. It is 1 over lifetime basically, right. So, I needed some quantity with dimension 5 multiplying that, and what else could it be other than the mass of the mother here to the power of 5. Okay. So, see, this is different from the previous case where we had a coupling that had positive dimensions. So, we had the mother's mass sitting in the denominator, but now we have a coupling of negative dimensions, right, and it had to be squared again because it is in the rate, right. So, to compensate for that, I have 5 powers of the mother's mass sitting in the numerator. Okay. So, this is how you do sanity checks to check for a sensible expression for the decay rate, okay. And of course, the 192 pi cubed comes from phase space, alright. Okay. So, let me wrap up this class by writing down what the actual lifetime of the muon is, okay. So, if you take this expression, alright, if I plug the value of Fermi's constant and then take the muon mass, okay. Once again, I very highly recommend that, this is MEV actually, very highly recommend that you do this calculation. See, the expression is right there, do this by hand, or if you are feeling up to it, go do it in Mathematica or something. You can even do it in just your Mac terminal or something, okay. Get a feel for these numbers, you have to do these calculations yourself, okay. So, you put all this in, okay, and then let me also give you the conversion factor. A GeV is 1.5 times 10 power 24 inverse second, okay. Putting all this in, you are going to get the muon decay rate to be 2.6 times 10 power 5 inverse second. Said differently, the lifetime of the muon, okay, which is basically 1 over the rate, that is it, right. The lifetime you are going to get as 3.8 microseconds, okay. and that is actually pretty good for this estimate, because experimentally, right, experimentally we find that it is actually 2.2 microseconds. So, what accounts for this discrepancy? It is just that I did not treat the phase space very correctly here, that is why I am putting an approximate symbol here. Okay, if I were to account for the correct phase space, because after all the electron does have a mass, I have to account for all that, right? I did not do any of that, right? I can neglect the neutrino masses, but I cannot neglect the electron mass here. If I put all those things in, I will get the correct value, but it is it's just off by a factor of 1.5 or something, so it is fine. Okay. Alright, so I will stop here. In the next class we will talk about proton decay, and then we will see some fun consequences of the dimensionality of time and how that affects the structure of decay itself. Okay. Alright, so we will deal with that in the next class. Thank you.